So how do you measure the temperature of something you can't possibly touch? I mean, think about a star millions of miles away, or the crazy hot plasma inside a fusion reactor. It's a huge challenge, right? Well, the solution is it's a brilliant piece of science. It's like we built a cosmic thermometer. This is a great explainer on the topic with notes put together by Sivaramakrishna Malapalli. Let's dive in and see how it works.
It's a really good question, isn't it? I mean, you obviously can't just stick a thermometer into the sun. So if you can't physically get to it, how on earth can you know how hot it is? Well, that's the central puzzle we're going to solve together right now.
Well, the answer, and it's a beautiful one, is hidden in the light itself. See, everything that's hot gives off light, and that light, it's like a unique fingerprint. It's packed with an incredible amount of information about where it came from, especially its temperature. All we have to do is figure out how to read it.
Okay, so here's the basic idea. We start with the light from that hot plasma. Now, it doesn't glow in all colors, only very specific ones. If you take that light and split it, kind of like with a prism, you get what's called a spectrum, a whole set of bright, sharp lines. Now, the brightness of each of those lines tells you how many atoms are buzzing at a particular energy level. And here's the real kicker. The way those atoms are distributed across all the different energy levels, that is a direct giveaway for the temperature. The hotter it is, the more atoms get kicked up into those higher energy states.
All right, so to turn all that information into an actual number, a temperature, scientists came up with this really elegant tool called the Boltzmann plot. It's basically a clever way to graph the data from those bright lines and pull out a precise temperature reading. It's a real classic in plasma physics for sure.
Okay, now this equation might look a little intimidating at first glance, but I promise, at its heart, it's just the formula for a straight line. You probably remember it from school, y equals m times x plus c. All that stuff we get from the brightness of a light, we bundle that all up into the y part. And the energy level of the atom, that's our x.
So here's how it actually works. For every single one of those bright lines we saw, we calculate a value from its brightness, and we plot that on the vertical y-axis. Then, we plot its energy level on the horizontal x-axis. If all goes well, those points should line up perfectly straight. And the temperature? It's literally hidden in the slope of that line. The flatter the line, the hotter the plasma. It's simple. It's elegant, and it's incredibly powerful.
But, as it so often goes in science, there's a catch, a little wrinkle. This wonderfully simple method, it works perfectly, right up until the moment it doesn't. Turns out this whole elegant tool is built on a hidden assumption, one that can totally fall apart in the exact situations we're trying to measure.
So what's the problem? Well, it's a process called ionization. You see, when plasmas get really hot, things get so violent that atoms don't just get their electrons excited to a higher level, they get them knocked off completely, ripped away. And that is where our nice simple model starts to fall apart. So here's the fundamental issue. Our simple Boltzmann plot assumes that the total number of neutral atoms we're looking at stays the same. It assumes it's a constant. But in the real world, in that intense heat, those atoms are losing electrons left and right. They're turning into what we call ions. They're not the same thing anymore, and that means our so-called constant number isn't constant at all.
Let me paint a picture for you. You start with a perfectly normal, neutral atom, let's say iron, which scientists label as FeI. The superhot plasma smacks it with a ton of energy, and poof, one of its electrons gets knocked clean off. What you're left with is an iron ion, which we call Fe2, plus that free-floating electron. The atom itself has fundamentally changed.
So, okay, why does this mess everything up? Why does this ionization process throw a giant wrench into our temperature measurement? How does it actually corrupt the data?
Well, it all comes back to that simple y equals mx plus c equation. Remember the c part, the intercept? The number of neutral atoms we're observing is baked into that value. The whole method depends on c being the same for every single data point we plot. But since ionization is changing the number of neutral atoms, our c value is no longer constant, so our beautiful straight line, it starts to bend. It warps into a curve. And that means we get the wrong slope, which leads us to calculate the wrong temperature. Game over.
So what do we do? How do we fix this? Well, this is what science is all about, right? Refining our models to better match reality. And to do that, we bring in a much more powerful tool, the Sahai equation. This is what's going to let us fix our plot and account for all that ionization.
The Sahai equation, it's another one of those foundational ideas in plasma physics. You can think of it like a recipe, or maybe a rule book. It tells you exactly what the ratio of ions to neutral atoms should be in a plasma based on its temperature and density. It lets us calculate that balance perfectly.
So to see how we actually apply this, let's take another look at the y-axis of our plot. This was the value we used for that first simple plot, the one that only worked for neutral atoms.
Now, for the corrected version, we add a whole new piece to it. This extra part, which we calculate using the Saha equation, is called the Saha correction term. What it does, mathematically, is account for all those atoms that got lost when they became ions. We are essentially putting them back into the equation for each data point, which forces that y-intercept to be constant again.
Of course, as they say, there's no such thing as a free lunch. This much better, more rigorous method needs more information to work. To even calculate that Saha correction, we need to already know two things: the plasma's electron density, and we need at least a ballpark guess for the temperature to get started.
And this is the payoff. When we apply that correction, what it does is it mathematically shifts our data points up or down. Those points that were starting to curve away, they get nudged right back into a perfect line. And the result is a beautiful, accurate, straight line. The slope of this line gives us a much more reliable measurement of the true temperature.
You know, this whole thing brings us to a really crucial idea in science. It's almost never about one method being good and another one being bad. It's always about understanding the limits of your tools and picking the right one for the specific job you're trying to do. And you can see the trade-offs right here. The standard Boltzmann plot, it's simple, it's fast, but its accuracy is limited, especially if things start getting ionized. It's great for stable, cooler plasmas. The SAW-corrected method, on the other hand, is way more rigorous and absolutely necessary for hot, messy plasmas. But its accuracy hinges on having good input data in the first place. You see? Each one has its place.
So really, context is everything. That simple plot is a fantastic tool. It's a quick and effective approximation when the conditions are right. But when the heat is really turned up, when reality gets complicated, you have to switch to the more robust model, the corrected plot, if you want to get an answer you can actually trust. And that kind of leaves us with one final thought, doesn't it? This whole story is about scientists finding a hidden assumption in their work and then building a better, more accurate model to correct for it. It really makes you wonder, what are the big, unstated assumptions we're making in our science right now? And what incredible corrections are the next generation of scientists going to discover?